Okay, ladies and gentlemen, take your seats. Think we're ready? Is that working, Bill? Okay. Think we'll get the meeting started? Hello? Hello? I can hear it. Okay, so I have to speak up. I can do that. Now, that's better. Okay. Apologize for starting a little late. We actually took our technical person. He had something he was involved with early, so we took some time away from him. So we'll get going. Don't blame Chris. Hey, I'm short. Blame me. Oh, gotta get the projector turned on. Otherwise, I don't know what I'm doing. Well, I don't know what I'm doing anyway. Hey, I see the little thing down the bottom coming up. All right, I think that's bright enough. Let's go to the first slide. Welcome to the Fort Worth Astronomical Society, May 19th, 2026 general meeting. Yay! All right, next slide. Okay, any visitors? Just kind of visiting in here. Do we have the portable mic? Just a sec, we're going to visit. We'd like to know your name and what brought you to us. How you found us.
Check. All right. Ready? Okay.
Small chairs with small mounts.
Do what now?
Small chairs with small mounts.
Yeah. So my name's Tim. That's throwing me off a little bit, the delay. But anyway, my name's Tim. I'm from Keller. This is my stepdaughter Crystal, and I'm into astronomy, and I just kind of Googled some clubs in the area and saw this. So I just wanted to come out, and she's into it as well. So we're happy to be here, and look forward to meeting you guys and seeing what the club's all about. So
Welcome.
I've got a set of binoculars, and then a small refractor that I bought. But I'm just learning to navigate. I was actually talking to. Oh yeah, I was talking to Bill about it, and I'm trying to navigate manually because I want to learn how to find things. So we're just kind of discussing the go-to mount versus the manual mount and things like that. So I'm here to learn. So
Great. Cool. Thank you. There is a wealth of information in this room. There is a huge wealth of information that aren't here right now. So
yeah, I mentioned I was going to be here, Bill.
yeah. Oh yeah. Next, I saw another hand up. Visitor back there in the back.
Jim Smith, live in Aledo, been living in this area for about 36 years or so. I was into amateur astronomy when I was a kid, and pawned my telescope when I was in the Air Force a bunch of years ago, and thinking about getting back into it. So that's it.
Welcome. Yes. Well, we got another one right here. Wait a minute. Wait for the mic so we can hear you. The online people can hear. There you go.
Danny Townsend. I was a member here about 25, 30 years ago. Back when we were in the astronomy, the museum. Yeah. And anyway, I'm not a member now. I have seen your new site twice already. And anyway, I've been out at 3RF for about 15 years. It's now 3RR because the college in Lubbock owns it. Anyway, I run the 30 out there, the 30-inch Dobsonian, and I've done that for about 15 years, I guess. So if y'all have been out there, I've seen you. I don't remember your faces hardly, but I do know Russ Boatwright. He's a good friend of mine and customer. But yeah, I've run a scope out there for the public, and I'm pretty handy with other scopes too. So
Great. Great. Thanks for dropping by. Yeah, he'll get it from me. I think that's it, Bill. All right, let's go to the next slide. Okay, please welcome our new, excuse me, our new members. Are any of the new members here tonight? Hey, we got one. There he is.
I'm the middle guy up there. Okay, next slide.
Okay. All right. Well, this society was founded in 1949. Most don't know, there's 405 individual members. You know, we have family members in that, so that kind of moves the numbers up to 245 accounts. We're also the largest astronomical society in the United States, which is kind of interesting. Our club members are wide range in experience. I mean, from binoculars to sun, it just goes on and on and on. I joined the club, I learned a lot, so everybody does do that. We have many members who are willing to help. I usually tell members, you know, if you go to the sites and you've got somebody that's really been over concentrating, find somebody else. Because most of the time they'll stand up, but every once in a while, some of them will bite and then they'll come and apologize later. Our club is a nonprofit organization. So feel free to make donations. It helps the club. Next slide, please. Okay. Our mission is to promote astronomy via public outreach. We have a lot of outreach programs that we are involved in to encourage and support groups interested in astronomy, and that goes along with the outreach program. To cultivate observing and research among members, to promote building of astronomy instruments and make club equipment available to members. So we have equipment that we will loan out to new members. And there are a lot of it's at the Rising Star, which is a dark site, so you just come out. You don't even have to carry it there. It's there for you to use. Next slide. Resources, we have a lot of handbooks. If y'all bought raffle tickets, there's a lot of books up here in the raffle. The Thompson Observatory, the Rising Star Observatory area is available. Club telescopes and eyepieces. Also, the club is online, and there's a lot of information available through Night Network that is available to the club as well, club members. Next. Okay, this is our dark site. This is what we're really proud of. It's out, we call it Rising Star because it's close to Rising Star. For me, I live up by the racetrack. It's 169 miles for me. People who live in Fort Worth, you're a little bit closer. It's easy to get. You'll need some guidance. So call a club member, find out who's going out there, and they'll show you where it's at. There are observing pads that are available to club members. We have the observatory, the Noble, and the McCarthan. Then the astronomy building where all of our stuff is stored. Also, there's 2 bunkhouses there. So if you want to spend the night, we have accommodations there, but you have to make sure that nobody else has got it ahead of you. We've incorporated RV parking area. You're kidding. All right. Whoa! Where'd that come from? Okay, way down here. I was always taught when you use a mic, it's supposed to be like you're drinking beer. But not with this one. All right, so we got the RV parking area. You have to sign permit, $60 a year, and just follow the policies. Maintenance buildings where the lower and everything. We have people that volunteer to keep this nice and mowed and cleaned and taken care of. Next slide, please. Okay, there's the list. There's a list of some of our telescopes. We have a lot more than these. We don't have them all listed up there. And we're still filtering out some that we've had a tremendous donation, and so we're trying to filter out what's going to be usable and what's not. We're still working on that. As you can see, there's quite a few, and there's some pretty good scopes out there. Next slide. Online resources. As you can see, there's quite a few areas that you can go to. And by the way, these are all listed on our website, and this will be posted. This video for this meeting will be posted, so all those will be available. And like the smart ones, they're using their cameras to capture the screen. Way to go. Next slide, please. Okay, additional info. Again, 2 more major sites. Now, me as a beginner, I've only been at this for 2 years. So I lost this. Okay, I lost that mic. I learned through this club, and I've always said, YouTube is your friend. But you have to filter out the guys that really don't know what they're talking about. Next slide, please. Bill, you want to introduce your speaker?
Thank you. All right. Yeah, it's kind of freaking me out. Can you hear me? Check, check. Okay. So Dr. Karen Sandstrom, she received her PhD in astronomy and astrophysics in 2009 in Berkeley, California. She moved to Germany as a researcher in the galaxies and cosmology department at Max Planck Institute for Astronomy. She was awarded a Marie Curie Fellowship from the European Union. She moved to Stewart Observatory in Arizona and then became full professor, where she is now at the University of California in San Diego in the Center of Astrophysics and Space Sciences. So she studies the interstellar medium and star formation in multiple wavelengths, and I'd like to introduce you to her. Take it away.
Great. Hi, everybody. Can you hear me okay? Oh,
Yes.
awesome. Let me just pull up the slides. All right. Is that coming through all right? Hopefully so. I don't think I can hear you, but hi, everyone. It's very nice to virtually meet you. My name's Karen. I'm a professor in astronomy and astrophysics at UC San Diego, and really excited to be here today to talk to you about my absolute favorite subject in astronomy, which is interstellar dust. I hope when you leave this talk, you might be just about as enthusiastic about dust as I am. So to start off, what I'd like to point out is that in between the stars in a galaxy, there's this very low density mixture of gas and dust. We call this interstellar medium. It's very low density on average. So on average, there's about 1 particle of hydrogen every cubic centimeter in a galaxy. But depending on where you are, there may be quite a bit denser regions. And those dense regions of the interstellar medium are very interesting because they are the locations where new stars form. And the interstellar medium is kind of the guts of a galaxy. It's where all of the most exciting stuff is happening, in my opinion. So the interstellar medium is the place where clouds of gas get dense and cold enough to collapse under their own gravity and eventually form new stars. The interstellar medium is also the place that at the end of a star's life, when it goes through the final phases, either as a supernova for a massive star, or as a planetary nebula or an asymptotic giant branch star, it deposits the material it's created, so the heavy elements that have been made in its interior over the course of its lifetime, deposit those back into the interstellar medium. And a large fraction of the heavy elements that stars make are in the form of dust. So my job and my focus in research is trying to understand the nature of that dust. And so my plan today is to tell you a bit about how we learn about dust and what the latest things we're finding out are, because right now is kind of a golden age for studying dust due to the relatively recently launched James Webb Space Telescope. So I thought I'd start with talking about a little historical perspective on how we knew there was dust out there, because without some work of folks reaching back to the 1700s or even earlier, it wasn't entirely obvious that our galaxy was full of dust. So when we look at this beautiful image of the Milky Way disk across the sky, the main way early on we understood that there was dust out there is because of the way it blocks light. So in the optical part of the spectrum, dust is very effective at blocking light. And what you can see here is a bunch of patchy regions spread over the disk of the Milky Way that are a bit darker than their surroundings. And these are places with clouds of dust and gas where the light is being blocked. So some of the first research in this area was actually done by William and Caroline Herschel. And interestingly, they were not aware that there was a bunch of dust out there, but instead what they were cataloging was what they called holes in the sky. So you can see a really clear example of one of these in the image in the middle. I think I can point at it. So the image in the middle of this diagram, this is a dense cloud of the interstellar medium that's relatively nearby in our galaxy. And the dust in this cloud is blocking the light from all of the stars in the background from getting to us. So it looks a bit like a hole, but it's actually not. It's just a dusty cloud in the foreground. But William and Caroline Herschel made a catalog of what they called vacant places or holes. And Barnard 68, this cloud here, is one of the most dramatic of those. So you can see their exclamation, "Here is truly a hole in heaven." But in fact, this is dust. Dust in the optical part of the spectrum really stands in the way of seeing the structure of the Milky Way because it's very effective at blocking light. And they attempted to make a map of what the Milky Way looked like by counting up the numbers of stars they could see in various directions in the night sky. And this is what they came up with. So the star in the middle, the yellow star, is approximately where the sun would be. And I think you can probably tell that this is not really resembling what we think the galaxy looks like. These edges and these features you see in this map over, I hope people can see my cursor over here. These are not actually structures in the Milky Way. These are places where there is a cloud of dust that prevents us from seeing very far into the Milky Way. So a number of years later, after more understanding of the nature of our galaxy, but still working in the optical, there is a very important measurement made by Robert Trumpler in about 1930 that helped to demonstrate that the stuff that was blocking light was actually dust. So what Trumpler did was to look at star clusters like the one you see here and assume that to the first order, all star clusters are basically the same thing. So they have the same color, the same luminosity, and the same size on the sky. In detail, that's not 100% true, but for the purposes of this experiment, it was fine. So what Trumpler found is that when you see a cluster like this that appears small on the sky, so suggests that it's far away, it also appears fainter than you would expect, just based on how far away you think it is, and it looks redder. So the more distant clusters that he observed were both fainter and redder than you would expect compared to the nearby clusters. And you might be familiar with this effect of blocking light and making it look redder from going out on a dusty or smoky day and looking at the sun. So one of the key features of small dust grains, or in the case of smoke, small particles of smoke interacting with optical light, is that they are much better at blocking blue wavelengths than they are red wavelengths. So it makes things look red or reddened. So from this observation, Trumpler concluded the following. So interstellar light absorption may be a consequence of light scattering by small particles fine cosmic dust thinly spread through the vast spaces occupied by our Milky Way system. And this is correct. And I also love that, back in the day, papers were much more poetic than we might put it today. But this is a really classic observation that demonstrates that there is dust out there in the interstellar medium. So before we get into kind of current research, I want to give you a few reasons why you might care about understanding things about interstellar dust. So I'll start with my main reason, which is that dust is absolutely critical to how galaxies work. So in particular, dust is very important for the process of forming new stars. So this is for a few reasons. The first one is that most of the gas in our galaxy, the balance between heating and cooling, so the processes that determine how warm the gas is, are controlled by dust grains. So this is primarily through what's called the photoelectric effect. And stars produce UV photons that dust grains absorb, and they eject an electron through the photoelectric effect. And this goes on to heat up the gas. So dust actually sets up the conditions throughout the ISM through this process. In denser regions of the ISM, it is also responsible for shielding the cores of clouds where stars might form from that same UV radiation. So dust is really good at blocking UV radiation. And if there's enough of it, it absorbs all that radiation on the outskirts of a cloud. And then on the interior, it can get really cold. And a cold, dense cloud is exactly what we need for star formation to happen, because basically we want gravity to win over pressure, which is pushing back against gravity. So if we can get the gas really dense and cold, that's the perfect setup to have gravity win and have these clouds of interstellar gas and dust collapse to form stars. So the shielding is a really important aspect of that. And then lastly, the same UV photons that the dust grains have absorbed, either in the process of blocking the light from getting to the denser cores, or just throughout the galaxy where they absorb the light very efficiently in the UV, they take that energy, heat up the grains, and then re-radiate it in the infrared. So they have a temperature, the dust grains have a temperature typically of around 20 Kelvin in the interstellar medium, and they produce emission in the infrared part of the spectrum. So this emission lets us trace where all the dust is. It lets us trace regions where the UV radiation from newly formed stars is very bright. And so it's a really important tool we have for understanding how galaxies work. So these are the dust is critical to the ISM reasons for why you might care. But there are a bunch of other reasons too. One of them is that we actually have to look through dust for almost everything we want to see in every astronomical object we want to see. So once we are outside of the solar system, there is dust everywhere, and there is also dust in the solar system. So dust is always in the way of the observations you're trying to make, and we have to correct for that depending on what the thing we're trying to measure is. So this is a map of our galaxy with the disk of the galaxy arranged along the middle of this projection. And the color table is telling you where there's a lot of dust and where there's less dust. But even if you look straight out of the poles of our galaxy, perpendicular to the plane of our galaxy, there's still lots of dust in the way. So we have to correct our observations for these effects. And this is true not just for optical observations or UV observations. Even when we look at very long wavelengths, like this is a map made by the Planck telescope, which was looking at millimeter wavelengths, there are important effects from dust on what we observe. This is a map that was made tracing out the polarization of emission in the millimeter and submillimeter part of the spectrum. And these swirly lines that you see on this image, which is very beautiful, are the result showing where there's polarization of the light. And these swirly lines trace the magnetic field in our galaxy. As it turns out, dust grains are not spheres, and they align themselves along the magnetic field, and that provides polarization both for the light they emit at long wavelengths and the light they absorb at short wavelengths. So dust grains have all sorts of effects on astronomical objects at all kinds of wavelengths. So in order to correct for those, we have to figure out all of the properties of dust that are relevant. Another important reason why you might care about dust is the emission that it produces in the infrared is actually one of our best tracers of galaxies all over the history of the universe. So you might be wondering why I'm showing you this image that looks like static a little bit. It looks like noise. But in fact, every little blip in this image is a distant galaxy. And this is a region that was observed with the Herschel Space Observatory. And there are so many distant galaxies in this region that each of the little dots from each of these galaxies blurs together into something we call confusion noise. There are just so many galaxies out there emitting in the far infrared that our telescopes can't separate them all into individual measurements. It's this background of emission that comes from galaxies in the infrared. So infrared emission from dust is one of our best tracers of both the interstellar medium and the history of galaxy evolution. And so lastly, there's kind of a more self-centered reason that we would want to understand about things about dust. And that is because that in the interstellar medium of the Milky Way and other galaxies, a large fraction of all the heavy elements, and that means everything heavier than helium, are in dust grains. So essentially all of the iron is in dust grains, a really large fraction of oxygen, carbon, magnesium, silicon, all of the interesting elements that are very important for life and the formation of planets and our existence were in interstellar dust grains before they were in planets. So tracing how we get from the interstellar dust to disks like this illustration of a planet forming in a disk around a young star to life is a really important path. And just as that was a previous image was a artist's impression, but this is not. This is actually an observation from the James Webb Space Telescope of a disk around the nearby star Fomalhaut. And what you see is a ring with a little blip over density here. It's barely able to be made out, but you can see it a little clearly in this zoom in. And this may be the signature of a planet that is in the process of forming in this galaxy's disk, or in this star's disk. And there are many, many stars that James Webb Space Telescope has observed looking at these disks. So dust is actually the thing that brings all of the elements together that we're interested in for planets and life. And so understanding it is an important task in understanding our cosmic origins. So with that, I wanted to tell you a bit about how we go about studying interstellar dust. And the first point I want to make is that for the most part, we are not actually going out and getting it. There is one exception to that, and there's actually about to be another. So there was a mission in the early 2000s called Stardust, which has this big, what's called aerogel. So you can see up in the top right corner. And in that is a gel-like substance that would capture dust grains as they impacted on this aerogel. So the Stardust satellite basically flew around the solar system with this aerogel and captured all the particles that landed on it. And based on the orientation of how those particles impacted the aerogel, they can tell if it's coming from the solar system or from the interstellar medium, which is coming in a very certain direction relative to the solar system. So Stardust flew around and then returned back to Earth. I think it landed somewhere in Nevada or Utah, I can't remember. And there were, in fact, 7 interstellar dust grains that were identified in the aerogel. One of them you can see with this arrow, this tiny little blip. Here's some, bigger blips that come from solar system dust grains, but interstellar dust grains are actually really tiny. And so it took a lot of work to identify these. And in fact, analyzing them is a very delicate process because they're quite small. So this was the one exception to going out and getting dust grains. There is actually another one happening right now. So it's called the IMAP mission. And there's an instrument on this satellite, which is now launched and out in the solar system, that is going to capture dust grains, and basically they'll impact the detector and vaporize, and they will be able to tell what they're made of and how massive they were. So they're not going to bring them home, but it is an instrument out there collecting dust grains. Other than those two exceptions, the way we have to study dust is purely through the way it interacts with light. So just as a reminder, the electromagnetic spectrum, the part we can see, visible light, is a very tiny wavelength range. You can see that illustrated here. Dust affects light over a huge range of wavelengths. So we'll talk a bit about important effects in the ultraviolet and in the infrared, but there's also a lot of stuff to be learned from X-rays and maybe even gamma rays and radio that I'm not going to get into. So when we're talking about understanding dust via its interaction with light, we have a couple of tools. The first of those is spectroscopy, where we break up the light into its constituent wavelengths, and we can look at the patterns of how bright a source is as a function of wavelength. And here's an example of the spectrum of two stars, one of which is hotter than the sun, an A star, and one of which is cooler than the sun, a K star. You can see the distinct behavior of these two spectra. Another tool we have is photometry, where we use a filter and capture all the light in a given wavelength range. And this lets us make images that are easy to compare at different wavelengths, where we've captured light and can look at the relative intensities at different wavelengths. So many of the images I'm going to show are collected in that way with photometric filters. And I think many of you are probably very familiar with this from a lot of amazing work you do with creating beautiful images of galaxies and nebulae. But often I'm going to be showing an image where the wavelengths of light that have been collected by a telescope and camera are not wavelengths our eyes can see. So here's an example. This is from the Spitzer Space Telescope, and it collects light in the infrared part of the spectrum. We can't see with our eyes any of these wavelengths, but a camera, infrared camera, can. And so it may, in this case, we have images at 3.6 microns, 4.5, and 8, and we can combine them just for visualization purposes into these beautiful images, such as you see here. So with that, there's a few important ways that dust interacts with light that I briefly want to mention. So we've already talked a little bit about absorption. So photons come along and the dust grain absorbs it and converts it into internal energy inside the grain. So it heats up a little bit. Another option is the photon comes along and then scatters off of a dust grain. And this phenomenon is actually what's responsible for things like reflection nebulae, which you can see a beautiful example here. This is the Pleiades. The blue nebulosity that surrounds these stars is a result of scattering by dust grains, redirecting that starlight towards us. And because of the wavelength dependence of how dust interacts with light, it's much more effective at scattering blue light than it is red light. The resulting nebulosity for reflection nebulae often looks blue because the blue light is much more effectively scattered. Lastly, a really important way we have to observe dust is through its emission, so the infrared emission that it produces. So everything with a temperature emits some light. For dust, the temperature is typically around 20 Kelvin. It can range up to a couple hundred Kelvin. In very extreme circumstances, it can be several hundred Kelvin or 1,000 Kelvin. But for temperatures typically around 20 to 200 Kelvin, the dust emits most of its light in the infrared part of the spectrum. And to give you an idea of what that looks like, here's a very familiar object. This is the Orion Nebula. And this is an optical image showing some of the beautiful structure of this, this region around the young stars of the trapezium. And I'm going to switch over to an infrared image, which is going to show you where all the dust is and where the dust is really hot and warm and emitting. And so you can see just how different the image looks in the infrared. So a lot of those features that are very dark and opaque in the optical glow in the infrared because the dust there is warm and emitting its own radiation. So infrared emission is great because that is actually a direct measurement of the dust. We're not waiting for, we're not using an absence of light as we do with absorption and scattering to infer something. We are directly observing the emission from the dust. And so infrared is one of our key tools for trying to understand dust. The main trouble we have is that infrared emission is mostly blocked by the Earth's atmosphere. So the Earth's atmosphere is nicely transparent in visible light, and it's also quite transparent in the radio part of the spectrum. But in the infrared, almost all of the light we would like to observe is blocked. So in order to observe infrared light, which is our best insight into dust, we have to send our telescopes to space. And there's now a long history of doing this. It started in the 1980s with the IRAS satellite, which had a 57 centimeter mirror and made some of the first wide area maps of the whole sky in the infrared. In 2003, the Spitzer Space Telescope launched. And this is a slightly bigger mirror, 85 centimeters. The really nice thing about Spitzer was that it was also actively cooled. So one of the important issues with infrared observations is that if your telescope has a temperature that is in the range of the temperatures of things you're trying to observe, so if it's emitting its own far infrared emission, you have to try to block that so you can see the astronomical objects you're interested in. So Spitzer had a lot of coolant and therefore had a limited lifespan reliant on that coolant to keep it cold and sensitive in the far infrared. And then in 2009, after Spitzer was finished with its prime mission, the Herschel Space Observatory was launched. This is a much bigger mirror, 3.5 meters, which is a huge leap forward. It was not as cold as Spitzer, but it was very sensitive because of that enormous mirror. I spent a lot of my time as a postdoc in Germany working with data from the Herschel Space Observatory, and I still do. It's an amazing telescope. But the end of its mission was in 2013. It was also limited by coolant. And so what do we do now? Well, we are very lucky that NASA has put together one of the most amazing observatories really you can think of, which is the James Webb Space Telescope. This was launched on Christmas 2021, and it is a 6.5 meter mirror. It's optimized for working in the mid-infrared, so not the far infrared. Those are the longest wavelengths. The mid-infrared is still excellent for studying dust, and it really is an amazing accomplishment. So first off, here's a little visualization of the mirror in one of the testing chambers, and you can just see how huge this is. The mirror is actually big enough, and the telescope is big enough that it can't be just put into a launch vehicle and launched like that. They actually had to fold it up, and this is going to be a visualization of the mirror unfolding and the telescope unfolding. So there's a number of just like incredible innovations that went into building this telescope, and the fact that it went like so seamlessly in deploying it was truly a major accomplishment for NASA and all of its partners. So what you're seeing right now is first the telescope as partially unfolded, and what's happening now is the deployment of the heat shield. So in order to keep JWST cold enough, it has to block as much sunlight as possible. So it has this tennis court sized heat shield, which consists of 4 layers that you saw deploy there. that blocks the sun. So that heat shield always has its back towards the sun, and then JWST is observing away from that. And you can see now the mirror deploying and unfolding into its final 6.5 meter form. So this is like the degree to which this went perfectly when it was launched is truly amazing. And here are some facts about JWST that hopefully blow your mind as much as they do mine. So first off, JWST is so sensitive that it could detect, were this a possibility, the heat signature of a bumblebee at the distance of the moon. It's also such high resolution that it can resolve the size, the angle it can see is the size of a penny held 24 miles away. So this is truly an amazing instrument. And here is a view of it at the last kind of moment it was captured after launch. And you can see the solar panels deploying. And the amazing thing was that they did not expect to see the solar panels deploy, but the launch was so perfectly placed that they were able to do this much earlier than they thought. And due to that perfect placement of launch, there's actually 20 or even more years of propellant. So JWST will operate for into the 2040s. So this is really incredible. And, you know, just to note, like, you know, there's a lot of worries about where science funding comes from and, you know, concerns about whether or not NASA will have the money it needs to do these kind of incredible things. And just, this is a, you know, amazing accomplishment to make this work. So having said that, what I'd like to do next is tell you a little bit about what we understand about dust and then some of the things we are learning from JWST. So first off, to clarify, dust is nothing like dust in your house. Dust in your house is kind of gross. I don't really want to, you know, be involved with that as much as possible. Dust in space is actually much more like sand or soot. So we think that there are primarily two types of dust out there, things that are made mostly of carbon and in fact resemble you know, some of the molecules and some of the composition we see in soot or smoke, and then things that are more like sand. So they're made out of silicon, oxygen, iron, magnesium, and they're a bit like the composition of sand. One of the types of carbonaceous dust, and this is actually my favorite kind of dust, is a very small dust grain, or some people would consider it a large molecule, that we call polycyclic aromatic hydrocarbons. So these are rings of carbon with hydrogens attached along the edge, and they produce very bright emission features in the mid-infrared part of the spectrum. It was first recognized that there were polycyclic aromatic hydrocarbons in space in the late 70s and early 80s with some of the very first observations that could trace the mid-infrared emission. And one of the amazing things that they found was that if you compare the spectrum, for instance, of the Orion bar, which you see down here, to the spectrum of auto exhaust, which is up here, there's some of the same chemicals. So polycyclic aromatic hydrocarbons are both in interstellar space and in auto exhaust. This led to a really great paper title that's one of my favorite paper titles. And for reference, polycyclic aromatic hydrocarbons are not something you want to interact with on Earth. They are very bad for you. So attempt to not breathe in polycyclic aromatic hydrocarbons as much as possible, but they are an important part of interstellar dust. The key properties we can use to describe dust are how much of it there is. So we call that the dust to gas ratio. So how much dust there is relative to gas. The size of the dust grains, what they're made of, and then some other properties that also matter a lot for the interstellar medium, but we're not going to get into much today. So that includes the charge of the dust grains and their shape and how well they align along magnetic fields. To give you an idea of how much dust is out there, one thing I like to point out is that if you took the interstellar medium and you compressed it so that it had the same density of air that we're breathing right now, it would be so dusty, in fact, that you would have a hard time if you held your hand out at the end of your arm, you would have a hard time seeing it. So there is quite a lot of dust in space, which is, yeah, a really interesting phenomenon. We can actually learn about the size of the grains primarily from how they scatter and absorb light. And this is pretty easy to understand if we just think about a quick analogy. So if you imagine waves on the ocean and a boat being the dust grain, if the waves are really tiny compared to the boat, like on the left, then they are fully blocked. So they can either be absorbed into the, they're destroyed when they run into the boat, or they reflect off of the boat. In that case, this is a very small wavelength compared to the size of the dust grain. On the other hand, if the wavelength of light is really big compared to the size of the dust grain, then the light just passes by like nothing's there. Kind of like how on the right, this boat is, the wave does not care about the existence of this boat. So this is exactly what's happening. Well, not exactly, but very analogous to what's happening with dust interacting with light. So if we have a spectrum of light incoming, things that are big compared to the size of the grain just pass through untouched, like the red light in this little cartoon, whereas things that are small compared to the size of the grain, like the UV or the blue, get absorbed by the grains. So from observations then of how dust interacts with light, we can see about what kind of size the dust grains have. So here is Barnard 68 again, at different wavelengths. So starting from the top corner, this is 400 some nanometers, 0.4 microns, and the wavelength increases as we go this way. So the wavelength is getting bigger and then bigger and bigger and bigger. And so you can see by the time you've gotten to 2 microns, it's basically like the cloud isn't there. You can't really see that there's any dusty cloud there. And that's because the dust is really bad at blocking 2 micron wavelengths, because that's much bigger than the size of the grains. So from this, we can actually learn that grains are submicron sized. So they tend to be around a few tenths of a micron. And here is a composite of Barnard 68, which if the projector there is pretty good, you might be able to tell that the stars around the edges that are just peeking through the cloud, the dust not quite blocked by this cloud, look red. And that is the visual representation of the submicron sized particles blocking light. So with that, I'd like to now move on to tell you a little bit about the life cycle of dust and what we have learned with JWST. So this is now a beautiful JWST image of a nearby molecular cloud in the near infrared, showing the light from stars, the big, obvious stars, and then scattered light from the cloud in the background. So dust grains their life cycle is really fundamental, but there are still a lot of mysteries about how they form and how they're destroyed. One thing we know is that old stars, what our sun will eventually evolve into, so this is called an asymptotic giant branch star, eventually moving on to a planetary nebula phase. We actually know dust can form in those situations. So here's a beautiful JWST image of the Southern Ring Nebula. So this is a planetary nebula. It's formed when, as a star evolves, it kind of loses hold of its outer envelope, and it sort of drifts away, revealing the core of the star in the center. And in this outer envelope, the gas is really dense and warm, and it's very rich in heavy elements that the star formed, including things like carbon and oxygen. And these conditions are actually the perfect conditions to form some dust grains. So what you want is a lot of the constituent elements like carbon and oxygen. You want them to collide a lot so they can agglomerate into bigger molecules and then grains. And you don't want it to be too hot so that when they run into each other, they don't break apart. So evolved stars and planetary nebulae are actually one of the best places to form dust grains. Here's another beautiful JWST image of another evolved star. This is actually quite a different type of evolved star. This is what's called a Wolf-Rayet star. And this is a massive star that eventually will explode as a supernova. But before doing that, it also expels its kind of envelope and forms dust in this outflowing, warm, enriched material. So we do know then that old stars are a great place for the formation of dust. However, some of those old stars, if they're massive enough, when they die, they explode as supernovae. And supernovae both form and destroy dust. So this is a really cool image showing the Cassiopeia A supernova remnant. And what you see in blue is X-ray emission. Infrared is kind of green, and optical is red. I may have that a little bit backwards, but the blue is certainly X-rays. And what you can see in this image is the remnant of a star that has exploded as a supernova. And the blue emission in X-rays is actually tracing the surrounding dust that's being destroyed by the shock wave the supernova has produced. But on the interior, the infrared emission is showing where there is new dust that has formed. So this is a relatively old image of Cassiopeia A, and the James Webb Space Telescope has relatively recently provided a new look at this supernova remnant. And you can see that here. So all of the emission you're now seeing is primarily coming from either new elements that have formed or dust grains. And there's a huge amount of detail here that has revealed a lot of different compositions of and types of dust that have been made. And I just want to zoom in because it's really incredible. This green thing here is a certain type of dust that emits brightly at these wavelengths, but you can see all this amazing structure, little bubbles and shells within this big filament, and this comes about from little nuggets of material that has been spewed out by the supernova. So here, zooming over here, we see a different composition of dust that's traced by these observations and some of the filaments near the shock wave from the supernova. So one of the things that's interesting about tracing dust with the mid-infrared, though, is that it's actually quite warm dust. And from what we can tell, even though supernova have, definitely made dust, they haven't actually made that much warm dust. So it turns out that we need to go to longer wavelengths into the far infrared or millimeter part of the spectrum in order to detect the cool dust. And to do that, we can use, instead of the James Webb Space Telescope, an array of telescopes called the ALMA, Atacama Large Millimeter Array, or ALMA, which is around 60 telescopes that operate in the millimeter part of the spectrum. They are at around 18,000 feet elevation in the desert of Chile, and they operate all of these dishes together in what's called an interferometer. ALMA is very sensitive at long wavelengths of the far infrared and millimeter, and this is precisely where, if there's cold dust, it would be emitting most of its light. And so to zoom in on a recent supernova, here we see supernova 1987A, which is one of the nearest recent supernova that's occurred in our neighbor galaxy, the Large Magellanic Cloud. And you can see a detection in this circle. This little point source was observed with Herschel. Zooming in, this is the visible light in that region observed with the Hubble Space Telescope. And you can actually see in the middle the supernova remnant that's growing down there. So ALMA observed this and found that there's a concentration of newly formed cold dust right in the middle of this supernova remnant. So this really demonstrates that, in fact, the supernova is making quite a bit of dust. In this case, nearly the mass of the sun in dust, which is very exciting. So supernova definitely make dust. However, they also destroy it, which is interesting. So they evolved for a long time with this shock wave that goes into the interstellar gas and dust. And when that shock wave encounters pre-existing dust out there in the ISM, it can actually shatter those grains and destroy them. And this is an observation of a supernova remnant from a supernova that occurred in the year 1006. It was actually recorded in some ancient records. And this supernova, we can actually see the dust destruction along the edges as it interacts with interstellar gas. And it turns out that on the whole, a supernova probably can destroy about 10 times more dust than it makes, which means that they are a net sink of dust in the end. So putting this all together, so far we have a couple of ways we can form dust, and one we can destroy it, one very effective way we can destroy it. We actually think that there has to also be the growth of dust grains in the interstellar medium itself. So that can occur by pre-existing grains having stuff stick to them and grow in dense clouds. And this observation by JWST actually reveals that through the fact that the grains they can observe in this cloud are much bigger than what we think exists in a normal average location of the interstellar medium. So this suggests that the dust grains are growing as they get into these dense regions. So my particular love is trying to understand how the life cycle of dust changes when we look in other galaxies. And in particular, I really like a galaxy called the Small Magellanic Cloud, which is only visible from the southern hemisphere. And you can see it up here. This, hopefully you can see my cursor, but this is the Small Magellanic Cloud. It has a neighbor, the Large Magellanic Cloud, down here. And these are two dwarf galaxies that are on their way in for a first close encounter with the Milky Way. So they orbit each other, and they are going to swing by for one quick pass pretty close to the Milky Way. So this is a beautiful image of the Small Magellanic Cloud made with Herschel. And what we have learned about this galaxy is that compared to the Milky Way, it has a very low amount of heavy elements. So it's around 5 times less oxygen, for instance, relative to hydrogen than we have in the Milky Way. And there's even less dust. So if you take a chunk of the ISM in the Milky Way and a comparable chunk from the Small Magellanic Cloud, there would be 10 times less dust in the Small Magellanic Cloud. This is important because early on in the history of the universe, all galaxies started off with a low amount of heavy elements. And just over time, when more and more stars form, they build up that amount of heavy elements and dust. So the Small Magellanic Cloud, our nearby neighbor, is like a good representative for what galaxies were like early in the history of the universe. And my particular work is actually investigating the abundance of polycyclic aromatic hydrocarbons in this galaxy, which turns out to be even less than a factor of 10. So the SMC, the Small Magellanic Cloud, has a very low fraction of dust in the form of these big molecules. And that actually has important consequences for how the ISM works throughout the galaxy. Here's a beautiful recent image of a region in the Small Magellanic Cloud observed with the James Webb Space Telescope. So this is the NGC 346 nebula. And it's a very massive star-forming region where there's around a big cluster of stars here and another big cluster here. And there are many, many O stars that will soon, I mean, not in our lifetimes, but will soon explode as supernovae. So just to kind of mention why I care so much about PAWS, this is a little animation of the process of photoelectric heating that I mentioned earlier. And of all the dust grains out there, the smallest dust grains and the polycyclic aromatic hydrocarbons are the best at the photoelectric effect. In fact, they do 50% of the photoelectric effect that occurs in our galaxy. So when we get rid of those PAWS in low metallicity, low heavy element abundance situations, then the physics of the interstellar medium changes pretty dramatically. And building on that, I am part of a collaboration called FANGS, quite an acronym, I know, Physics at High Angular Resolution in Nearby Galaxies, where we are trying to understand star formation and the interstellar medium in nearby galaxies where we can nicely resolve all of the regions. And we have recently been observing these galaxies with the James Webb Space Telescope, leading to some really dramatic, beautiful images. So here is a view of NGC 628, I think it's M74. Although I always get the M numbers wrong, I apologize. I'm sure you all know this, so you can correct me in the Q&A shortly. What you see here is an image in the mid-infrared created with the James Webb Space Telescope. And in fact, almost all of the emission that goes into making this image is coming from polycyclic aromatic hydrocarbons, which are very bright in the mid-infrared part of the spectrum. Here's another beautiful galaxy from the FANGS survey. This one has a very strong bar, which is the linear feature you can see across the middle, and the gas actually flows along these lanes into the center of the galaxy where there's a big burst of star formation happening. Here is another beautiful JWST image, still looking at mid-infrared emission from PAWS. And combining all of what we've learned so far, we actually have a new picture of how PAWS behave in galaxies. So what I'm going to show you next is some evidence we found about the destruction of these small grains. So this is an image, just like I showed earlier, the color bar is showing you how bright it is. And I'm now going to show you a map of where the PAWS are. And what you can see is all of these little tiny bright dim dots, these dark regions throughout the galaxy. And those are places where PAWS have been destroyed. They have been destroyed by absorbing two energetic photons. So by that I mean the photons are too energetic. They're like UV or even X-ray photons that come from young massive stars, and the PAWS then break apart and are gone. So we have learned a lot already about the nature of PAWS in nearby galaxies, and this has been a result of the amazing images that JWST produces. So with that, I will wrap up and take some questions. So I want to leave you with a few takeaway points, which is that although it's only a small fraction of the mass of our galaxy, dust is actually critical for how it works. It's really important for the process of forming new stars. It's also the raw material for planets and humans, and most of the heavy elements that make up our planet and us were in interstellar dust grains when they were in space, outside of the solar system. Dust emission lets us study how galaxies evolve over the whole history of the universe. And I hope you agree, sure makes some really pretty pictures. So with that, I will leave you with a favorite quote, and I'm happy to take any questions.
That's,
Check.
thank you.
Test.
Bill? Oh, you back there?
Yep. Do you have any questions?
Could somebody get a light on? Any questions?
I'm not
Okay.
sure I can hear anybody. But
We got one coming. All right.
Dr. Sandstrom, if a person was interested in trying to understand more of the fundamentals about the work that you do concerning dust, what would be some, I'll say, credible places on the web to go look to try to understand more about this aspect of science?
Did you hear that? Okay. Can you hear us?
yeah, I can hear you now. Mhm.
Okay. You want to try that again?
Yeah. I was wondering if a person was interested in trying to understand more about the fundamental aspects of dust in the universe, where might be some credible resources to find so that what you read has, I'll say, credible science behind it, so you can get a better understanding of the fundamentals of some of this science?
Yeah, that's a great question. So, NASA, in fact, in the James Webb Space Telescope website on NASA has a lot of information. They have a great kind of background knowledge section on their website that would be a really nice resource for that. Um, if people are interested, I can recommend there's a free online textbook about astronomy that is really useful kind of at the starting point. And in fact, Wikipedia has really nice information about dust as well. But I think if I were doing this, I'd probably first go to NASA and go to the James Webb Space Telescope site on NASA's main website, and then look for some of the resources they have there, because they've designed a lot of stuff for public outreach that's really helpful.
Okay. Any other questions? Got one over there. All right.
Hi there. Thank you so much for your presentation. I enjoyed it. I just had a quick question. I know you'd mentioned the heavy elements.
Yeah.
And, I was just kind of wondering, the stars, they stop at iron, but I was thinking about like gold and tungsten and the heavier things. So it kind of gave me I kind of had a question when you mentioned, during a supernova, how the dust particles are destroyed, but my understanding is these heavier elements come out of either neutron star collisions or something like that. And are they not destroyed? And if they are not destroyed, then obviously they're not destroyed because we have the elements here. But what makes them not? How is it you're able to destroy the dust particles but not the heavier elements during that process, especially something as violent as a neutron star collision?
Yeah, that's a great question. So, in a neutron star collision, I think in fact, a lot of stuff is open for destruction. Out in the interstellar medium, when you're destroying a dust grain, that's really like breaking bonds in a molecule. It doesn't require that much energy. So, destroying an actual atom, which would be like splitting and fission, basically, requires a lot more energy in most cases. So, the nature of like destroying grains is not that you remove the atoms, it's just that you turn it from a solid particle made of some molecules into those constituent atoms back in the gas. But you're right, like for the very heavy elements, those are expected to mostly come from violent events like the mergers of neutron stars. And that makes those elements quite rare. So things like you said, they are not, gold, for instance, is not like a big constituent of dust. It's a very rare element out there in space and on Earth. Most of dust, the mass of it is in carbon and oxygen and silicon and iron and things that are much more abundant. I'm not sure if that answered your question, but
oh no, you did. I just had one more. Do you follow the same process as far as what light is blocked to identify? So if you saw some tungsten, it would block at a certain wavelength. Do you do the same process for dust that you would for the heavier elements then, is my question.
Yeah, so indeed, when we look for certain elements, we look for if it's an atom of tungsten, it would produce absorption feature. For instance, if we had a star and you're going through the light is propagating through the interstellar medium and there's like some atoms of tungsten available, they might have a signature of an absorption line at a certain wavelength or an emission line from that. For dust, actually, we kind of go from something where it interacts with light over many different wavelengths to things where dust spans sizes that are like actual pebbles all the way to molecules. So if you're talking about a molecule, it would interact with light at very specific wavelengths. But if you're talking about like a grain of dust or something macroscopic, it interacts with light at multiple wavelengths. So it's a bit different how we use that information about light interacting with stuff in trying to understand dust versus trying to understand like individual atoms that would be in the gas. So things like when they're in the form of individual atoms, they interact with light at very specific wavelengths that correspond to the difference in energy between states where you have the electron. So it's very specific energy difference, and that corresponds to a really specific wavelength. So hopefully that was clear. Dust can absorb a photon at many different wavelengths. It's best at absorbing the UV ones, but it can happily absorb an optical photon. And so we have interaction with light over the whole electromagnetic spectrum, really.
Okay, great, thank you. I think we got time for one more. All right, we good? Bill?
Dr. Sandstrom, thank you so much for taking your time to speak with us and share your expertise on this. I appreciate it.
My pleasure. Thank you for
Thank you so much.
thank you for the audience. And, yeah. Sorry I can't be there to meet you all in person, but yeah, look, thanks very much.
Thank you. Next slide, please. Raffle. Okay, let's start after a 10-minute break, and see you in 10 minutes. Okay, let's all take our seats so we get going with the raffle. Looks like we've got a lot of goodies tonight. And I'm going to bring the box over here since I'm doing the drawing and we've limited it to this cord. Hello? Yep, we're good. Okay. Let's get this show on the road. Okay. First number. Where are my glasses? Oh, it's upside down. Okay, 1, 5, 5, 3, 3, 2. Hey, we got a winner. Come on down. Pick out your book. Are these objects also? Okay. And you better hurry because I'm going to the next one and y'all can fight over it. That's okay. I trust you. I'm a trusting soul. Oh, my goodness gracious. Okay. Anything on the table? Except that light down there, and can't have that. 1, 5, 5, 3, 5, 0. Hey, we got another one. All right. Okay. I was going to shake the box and you grabbed hold of it. Okay. We got a 1, 5, 5, 2, 8, 9.
Yes.
Hey, got one. Oh, I'm going to let him go for it. Okay. Ta-da. And we've got a 1, 5, 5, 3, 0, 0. Oh, bring it on down. Oh, I'm digging and shaking. I tell you. Okay. I got down a little ways. 1, 5, 5, 2, 7, 9. Hey. Hang on a sec. All right, we got him shook. We shook him up that time. Okay. We get a stack of them up here fighting. I'll let one clear. Okay, let's go ahead. 1, 5, 5, 2, 9, 0. 1, 5, 5, 2, 9, 0. Oh, go ahead. Okay. He's got all he wants. Hey, it's your choice, man. Okay. We're moving on. 1, 5, 5, 3, 3, 8. 1, 5, 5, 3, 3, 8. Going. Hey, we got a new one. All right. Bring it on down. Anything on the table? I stirred that one up that time. Okay. How about 1, 5, 5, 3, 8, 1? All right, bring it on down. Now, don't take anything away from our new person. Okay, that's good. We're good. 1, 5, 5, 3, 7, 9. Oh, all right. Everybody's awake tonight. Let's go to the other side of the box. Get one down on the bottom there. Yep, we're good. Okay. Let these two old timer pros fight after it. All right, moving on. 155356. 155356. Check your tickets again. Oh, no. No, okay. Yep. Okay. 155309. Again. All right. Get on down here. I'm gonna pick one off the bottom that's been sticking down there. If I, oh, that one's all the way down. One 55340. One 55340. Okay, 155274. 155274. Oh, oh, got one hiding in the corner. There we go. 155331. 155331. Moving on. One 155380. Hey! All right, bring it on down.
I didn't know we had a count.
155317. 1553. All right, look at there. Double team in there. He's big enough to defend himself. I'm going to let him fight on it. Okay. 155323. 155323. All right. Man, I'm stirring these babies. I don't know. I think y'all sold duplicate tickets or something. 155360. 155360. At one point, did we just call it quits? And then take that away? How much time we got? 155314. 155314. 314. Oh, again. All right. Oh, yeah. Hey. There you go. You're going to pay for your membership pretty soon. Oh,
This is what I got.
I reached down and I bit one, so maybe. Yeah. 155368.
85.
One 155368. There he goes. I got to quit stirring them. That's what it is. Okay, one more, guys. 1111. 155327. Did it again. That's it. Come on, get the last one. Hey. Okay.
Thank you, Sam.
You're welcome. Last one. Oh, I love it. Well, what was the old series? I love it when a plan comes together, right? 18. Okay. Up next, we have our VP and What's in the Sky, Bill?
Thank you. Yeah, I got it. Okay. So this is everything that's going on in the sky above the clouds for the next month. And Mark Kozowski is very lucky to have caught the Omega Centauri. Next slide. Globular cluster, yeah, a rising star, not bad. It's just like that 5 minutes of clear sky there, so good shot. How low was it on the horizon? Something like maybe 10 degrees, if that. In the trees, it's a good shot, it's a good catch. Next slide. Okay, bright comets this month. So 2025 R3 Pan stars. Some called it the Great Comet of 2026, whatever. Well, at least Adam Block got to see it because he imaged this one. And now the next thing that's coming up, it's getting brighter, will kind of be our star comet for the summertime, is 10P Temple 2. Right now it's in Ukila, and it's about magnitude 10, but it's going to start brightening as we get towards the summertime. And of course, all of my insight about comets is at aerith.net. Next slide. And then there's 3 double transit of Jovian moons on the surface of Jupiter's atmosphere. One of them is May 24th, and it's Europa and Ganymede. From these times that's underlined right here is when both of the shadows are on there. It's a pretty cool sight. May 30th, same 2, and then June 9th, we've got Europa and Callisto, and they're all at nighttime or early in the morning, so catch one of those if it's possible. Next slide. And then that's next slide. Got to throw it in, right? I mean, you know, it hadn't happened yet. Okay, so there's a near-Earth object called 1943 Anteros. It is an asteroid going to be coming closest to the Earth on May 30th at probably about the closest that ever gets to the Earth. It's not a very big one, relatively speaking. It's about 2 to 4 kilometers in diameter. Shines at about 13.6 magnitude at brightest, and it stays that bright until June 4th. And probably what you'll see in the scope is point of light. You're not going to see anything tumbling or anything like that, but it's, you know, the closer these things are to the Earth when they're doing their flyby, you can actually sit there and watch the thing move. And that just, you know, gives you that sense of motion going on in space. Everything else isn't moving. Next slide. And the full moon, May's second full moon, the blue moon, is on May 31st. I want to feature this guy right here. This is actually a guy that he lives in the mountains in France. He images out of this massive telescope out of his backyard, and I follow him on Astrobin. His name is JP Brock, and he does these. I mean, like, any better of a picture, you'd be like an orbiter or something around the moon. But just amazing pictures. You ought to check him out. Next slide. Morning Venus at its highest actually gets pretty darn high at 30 degrees. Morning in the, okay, look at that. Well, so that happened. So either in the morning or in the evening. I think it's the evening this time. So do not look at the morning part. It's evening Venus at its highest. It's at 30 degrees in the evening on June 12th, and it shines at magnitude -4.3. Next slide. New moon in June is on June 14th. Next slide. And Mercury is in the evening. It reaches greater eastern elongation on June 15th, and it'll be highest a whole lot better than any of its highest points in the sky last year, at 19 degrees above the horizon at nautical twilight on June 11th, and at magnitude 0.4. Next slide. Okay, so this time we're going to be featuring a southern constellation called Antlia, the air pump. So we can identify that this is a concoction of Lacai's with his time on the Table Mountain in the bottom horn of a Cape what? Cape Town, yeah, down in at the bottom of Africa. So he spent a couple years down there, and while he was there, he made up a bunch of constellations, and this was one of them. So I looked it up years ago, and I was like, air pump, you know, when I first learned about Antlia. It was like, okay, well, what kind of air pump are we talking about? I mean, bicycles didn't even exist when he came up with this, let alone, you know, tires with inner tubes or anything. The first bicycles that came out had solid rubber. So, you know, what's this air pump? Well, it's an air pump for experimentation where you actually gives it, you have the capability of being able to remove air from a container. So a little more about that later. But it's got one named star called Macondo, and it's actually visible to us in the sky about this time of year. In April, it's about 20 to 25 degrees at highest at transit with the meridian. And incidentally, it happens to be just right above the Argo Navis, which I've been talking about last few months. Next slide. So there's S Antliae. This is an eclipsing contact binary. This binary is so close, these two stars are so close together that they actually share a common envelope, and their atmospheres actually touch. Their orbit around each other is 0.591 days. So that's it's eventually, not in our lifetime, but eventually it's going to merge into one star. Next slide. Then there's the Antlia cluster. Okay, so I've talked about galaxy clusters when I was talking about Virgo cluster, and other clusters in the sky with some of the constellations I featured before. This is the Antlia cluster. This is the third closest galaxy cluster to our local group, and it's after Virgo and the Fornax clusters. It's a part of the Hydra Centaurus supercluster. It's you know, like all galactic clusters, they're gravitational bound to each other, and this is a group of 254 of them. Interesting thing about this particular galaxy cluster is that there isn't a central dominant bright galaxy. So most of them have that. So they're not really sure what that's all about, but that's the case. Next slide. And this is a shot of said Antlia cluster via the Dark Energy Survey. Next slide. Then there's NGC 2997. So this is a big deal to Southern imagers and observers. Beautiful grand design, spiral face on, with an enormous amount of star formation, extremely bright nucleus. And it's the brightest galaxy in the NGC 2997 galaxy group, which is a member of the local supercluster. So when we talk about galaxy groups like, you know, the Leo triplet or Markarian's chain or Dirichlet group or anything like that, we're talking about groups of galaxies that are very significantly involved with each other gravitationally. So they're not clusters within themselves, but they're groups that are significantly involved with each other gravitationally that are part of a galaxy cluster. So next slide. And that's just a charmer right there. Next slide. Then there's NGC 3175. This is almost edge on, very prominent with dust lanes. Outside of its core, neutral hydrogen is almost absent outside of that, which is actually very unusual. There aren't any other galaxies anywhere in the area of this galaxy, so really they still don't understand why there's such an absence here. A galaxy collision could be a cause of that, but because there are no other galaxies in the area, they're not really sure how that's happened. Next slide. And that's Hubble shot. Next slide. And then there's index catalog 2560. So this is a type 2 Seyfert galaxy. Seyferts are actually known as to have quasar-like intensity going on in its core. It's like a quasar, but it's not a quasar. It's a black hole, but it's just got incredibly intense emissions. In non-visible wavelengths, it's an incredibly intense brightness. Next slide. This is a Hubble shot of that. All right, next slide. Okay, so I can tell you about this picture in a second. So for a listing of the 102 deep sky objects in Antlia, these are a couple of pretty cool websites to talk about. So go to the next slide. So when I did learn about Antlia, and I did a search, on Antlia and what the heck is an air pump, being that it wasn't for bicycles or anything. This was the first thing that I came on in my search. And I was like, okay, well, what are we looking at here? So this is a painting by a guy named Joseph Wright of Derby. And it was painted in 1768. So this is not long after the invention of the air pump. But yeah, what we've got going on here just kills me. It's like, okay, well, you're proving that the air pump works by putting a bird in the container and sucking all the air out of it and freaking out your kids, citing your scientist friends, but putting some of them to tears, very upsetting, dead birds and all that. So it's just really amusing to me. I thought I'd share it. Next slide. And this is a Whirlpool Galaxy by Sean Paul. Very, very nice. Yes. So keep looking up. Thank you. Do you want the lights on or off? Turn them off? They're already off. You want me to keep them off? You want to turn them on? Okay. Watch your eyes. You want them on? Okay, Constantine wants them on. Watch your eyes.
And then you can give him the mic.
Okay.
Thank you. Thank you, Bill. Sam. Right here? There we go. Okay, financial report. We've had lots of activity over this past month. Our current balance, as you can see, is a little over $46.6 thousand. We've had $67.90 in donations, over $10,000, of which was the purchase of the zero-turn mower. Looking at the bottom half of the page, the Rising Star Development Fund. Please note that our income from donations, $6,000, those are for primarily the mower, the rest of the monies that we didn't get last month, in addition to the $2,500 donation towards an observing terrace, which is a project that you're probably not aware of, but will be coming to you shortly. Expenses, $46.85. That's partly for the mower and also a string trimmer that we've purchased out there. We did make a substantial loan payment of $4,500, giving us a remaining balance of $9. This is on the loan. Any questions on any of this? As always, these reports are uploaded to Groups.io, and that information is there. Always feel free to reach out if you have any questions at all. But let's talk about this next page, which is important for next month's meeting. I did mention last time that there are some renovations underway at this facility, and UNT has requested that we relocate to a different room for our June and our July meeting and possibly our August meeting. And let me kind of get you oriented. We are in the Research and Education Building, RES. In June, we're going to meet in the IREB, which is the Interdisciplinary Research and Education Building. It is the building east of here, which is in that direction, I believe, across Clifton Street. You may park in the same parking lot that we're parking here, or you may park in the parking garage adjacent to the IREB. The best way to get to the room is to enter from the north side of the building, which is the parking garage side. Once you come in there, just walk down the hallway, be in room 250, which is on your right. It is a totally different arrangement than what we have here. Let's go to the next slide, please. As you can see, these are really set up as workstations, groups of 8, and there are monitors all the way around. We're still trying to coordinate to figure out how to interface with that, but it should be an interesting experience. There were some concerns about, is it big enough? Yes, there's 128 seats, so there'll be plenty of room. Hope to see everybody there because, of course, next month is our election. Okay, last thing I wanted to talk about was membership renewal. I've received a dozen or so renewal funds today, plus a number that have been mailed in or sent to us. So right now we have about 25% of our membership has renewed. We are 2/3 through May, and this is our renewal month, and we're only 25% of the way through. So please renew your membership. If you don't get to it in May, you'll have an opportunity in June. You'll hear from me again at that time. Comments, questions? Thank you so much.
Thank you, Constantine. Okay, let's go with the executive board on what we accomplished in our last meeting, and I'm going to hit these real fast. If y'all have any questions on any of these, come see me afterwards, because some of them could get lengthy. Anyway, we set the responsibilities for the Zoom meetings to the given parties, so we won't have that incident that happened where Bill have the correct Zoom meeting. Okay, this one. Okay? All right, we'll go with that one. Anyway, we took care of that, so there are specific people assigned the Zoom meetings, and that's under control. We're going to initiate, present, and accept. Okay, we're going to set up on the website. I wrote this, by the way. On our website so that we can take donations as well as our memberships and all that. We got that process started. We're going to be looking into the way that we do that. We want to keep it simple. I don't want any obscure third-party agencies that you have to join and give your life and your blood and your DNA in order to join them so you can pay. We're going to keep those out. We got the purchase approval for the push mower at Rising Star, which, you know, we have the right mowers to mow around the buildings where the big one can't get, and also keep the big one away from the mesquite trees because the little one has solid tires. I picked that up. It's kind of cool. You push the handle, it goes. You push it harder, you'll be jogging. So it's a neat mower. Harder you push it, the faster you go. We're going to create a architectural review committee for the new site and building rollout that we're going to be. That's still, he told me to use this one. So we'll be, as things progress, we'll be covering more details on how that's going. Yeah, the of hand mowers. Burial. How about this one? This one don't work either. Hello. Testing, 1, 2, 3. Okay. We have some mead scopes. The hand controllers are bad. We've authorized the purchase of the hand controllers to try and get these really cool mead scopes running. So that was approved. Then the decision on a committee to manage the club's donated committee going to lay them all out, work, or we can't fit. They're going. I don't know where. I hate it doesn't work to anybody. Up on that. But anyway, we works. When new people come out, scope they have trouble with. Decision, yeah, and then recognition of the party, the club party. We'll recognize him for bringing that up. Potluck, in case y'all don't know it. And the Caps Smith Park. And what's the date on it again? Hey, okay, and that covers that. Let's go to the next slide. Let's go to and I don't believe there's any other business in the business meeting. Do what? Okay. Elections. There you go. President. Absolutely. Come on. Give Cy some. By the way,
Okay, I'm Robin Pond. I'm on the nominating committee for the so far this is what volunteers and those who have been the treasurer is not listed. That was for treasurer for this year. We mistakenly did not realize that the treasurer, although he can serve for 5 years, must be elected every year. So he will be on there. Anyone who wants to run for an office, if you want to nominate for an office, you can do that, and this can be done up until at the next meeting. So anytime between now and when we cast our votes, you may put your name in the hat for any of these offices. Do we have anyone to run for an office?
oh, come on. Everybody. Come on.
Okay.
Come on. Member for 2.5 years, I'm president, okay? Don't for it.
Are there any questions? To run for an office, you have been of time in the answer here.
Here.
Okay.
Okay, is that it? All right. I don't see any hands coming. Everybody raise your hands. Announcements, okay. Monthly, go to the next one. Whoa, Acorn 2026. I didn't see this slide. Where did this come from? All right. August 12th to 15th, National Registration, happy hour. Take a picture of it. Put it in your memory banks. General upcoming events, no currently scheduled. Keep it rolling. On. Here either. Okay. We'll get. There's the Tandy Hill. Star parties, look at that for a second. Let everybody soak that in. All right. Young astronomers, no. Did you read the dates on the Tandy Hills? Well, on the screen. Okay, Saturday, May 23rd. Sunset, absolutely. My mind's not working that fast. All right, Young Astronomers Program, yay. Yeah, I just read what I saw. 16 Foundation, we're just zipping through it. No event schedule. By the way, summertime for them is kind of slow for us getting in there, but Tom? Well, sometimes we just have to let them get it. Yeah.
Hopefully the mic will work. And yes, Tom, after 10 years on the board for Palo Pinto Mountains State Partners, that supports the decided to take some time off, and so now I am on the board. And part of the reason we have been involved is to make sure that astronomy remains sight of those who are. We want to make sure they understand it's important, because we had at the park before they started construction, and they have some really nice skies. We had our first star party last Saturday, and I think Tom estimated 100 people who came through. Some of those were camping in the park. Some of those came from the Metroplex in both areas just for the star party. They had this nice little graphic, for star parties with sponsored by the Fort Worth Astronomical Society. And we had several members who came out. We had different types of telescopes. We had some with binoculars. Jimmy, who is one of the rangers out there, used to be a member of our club, and so he came out and he did a lot of different varieties for people to look at so that they could see, they could do it in right now, the night for a star party out at Palo Pinto is, and I think Patrick, is he still here? said that he had been out Monday at Palo Pinto. Good. So yeah, it's going to be a great time out there now that we've got things starting to work out there. So if you can join once I get that date firmed up with Kate, who is those events, I'll get an announcement. You've got that on your calendars.
There's dark skies. Yeah. Okay.
That they can count. That does not include people who come in and the gates close and they may not sign up. It does not count all the people they had to turn away. Because if you do plan on going out there, your pass to enter the park, they sold out of their day passes several days. They already put out a notice to go ahead and book your day passes now for Memorial Day, because the whole weekend will fill up quickly for the day.
Okay. Y'all didn't hear that Thursday. They can count, and if you want to go out there, book. Next slide. On Cross Plains, yay! That was started, and I have not. Maybe the next president. Okay. Cross Plains, there we go. Rising Star Observatory area. Tom, you wanted to cover some other stuff?
So basically,
Get over here. Do it right.
I'm Tom Schneider. I've been tasked with taking care of RSOA. I want to thank everybody for all your continued support and for Sam to get us all the equipment we need. We're set up basically for a decade out there. The other thing we've done, Dacia helped clear out the front storage container. Basically everything in there right now works. And he's also cleared out one of the bunk rooms. So that's available if anybody wants to stay out there. As we find out what equipment is available, we're going to move it into the front bunk room. What we want is systems, so somebody can come out, grab a scope with a mount and a tripod, take it out and use it. We're working on that. And then this Saturday the 30th, we're going to have the party in Watauga. It's just a party. It's not a star party. You're welcome to bring a scope. If it's cloudy, we'll still go ahead and do it. If it's raining, probably not. But it's a social party. We're kind of like nurses. We do everything for everybody else, but nothing for ourselves. I'm also working on scheduling a party at RSOA. We have this wonderful site out there, and we use it once a year, and it's normally canceled because of the weather. But I want to have more parties out at Rising Star. So as you guys, if anybody wants to help figure out what scopes work out there, have at it. When you get them working, let me know what the number is. I want to end up bringing a couple of those scopes into the Metroplex so that new members can use them. If you're a new member and you don't have a scope, let me know. We'll try to get you a scope. I actually have the 50 millimeter Lunt solar scope at my house, and we're waiting to get a case for it. As soon as the case comes in, you guys are welcome to borrow that.
And if I remember the info on the invitation for the 30th, it's potluck. If you forget to bring anything, don't worry about it. Those that do, then thank y'all. All right, next slide. Greg, website media, anything?
Nothing for this month.
Oh, the meeting starts at, the club event starts at 5 o'clock. Okay, he online? Okay, you got nothing. Okay, let's move next slide. You want to cover it? Sure.
Thanks. So this guy, he's going to be speaking to us next month. He's actually going to be in town, so he's actually going to be in person. And he studies extreme pressures and the physics of planetary cores. It's kind of a thing I'm going for, just kind of some different things that we don't always think and talk about. So be here next month.
Oh, you bet. All right, next slide. Okay, after the meeting, some of us get together. We go down to the social club. It's just down the street. Have some beers, have some appetizers, just chit chat. No big deal. We're trying to take over the place, but we haven't got enough people down there yet. But there's the address. Like I said, it's what, a half mile, maybe 3/4 down into town. And next slide. Hey guys, thanks for attending. See y'all next month.